Hi, Year 13. Today's lesson is on friction, so we're going to move forwards with our forces at an angle chapter and put friction into the mix, and we're going to figure out how to calculate it. So firstly, if we think about what friction is, so it's obviously a force that acts between an object and a surface, and if the surface is rough, which you're going to look out for in a question, then there's some friction opposing movement there. So it depends on two things. So the amount of friction that exists between the object and the surface depends on these things here. It's the normal reaction between the surfaces. So an object that's heavier is going to experience more friction as you try and push it along. And also this number called the coefficient of friction between the two surfaces. So this is basically just a measure of roughness, if you like. And it depends on how rough the surface is. And it's this constant that we typically call mu, which is the Greek letter m. Okay, and normally this number is quite small. It's normally between 0 and 1. Okay, right. So the maximum frictional force is calculated as follows. So there's a sum for this, and it's nice and simple. It's F max is mu times r. Okay, so you just times those two things together. So what that means is that this number F max is the greatest amount of friction that could possibly stop your object from accelerating. Okay, if your force is less than or equal to this value, then friction is going to oppose it equally in the other direction. And if your force exceeds this value, then your object's going to accelerate because it's enough to overcome friction. Okay, and then smooth surfaces obviously has no friction, so we take the value of mu to be 0 in that case. Okay, right, let's see an example then, so you can kind of see what I'm talking about. So all this stuff here can go into a picture. A block of mass 5 kilograms. It's at rest on a rough ground. Rough is kind of indicating to you that we're going to use friction. The coefficient of friction between the block and the ground is 0.4. A horizontal force is applied to the block, and then find the magnitude of the frictional force when the acceleration of these, when the force, is this particular value. So 10 newtons, 19.6, and 30. Right, the picture's going to help us out figure out what to do. So here's your block, 5 kilograms. The weight then is going to be 5g newtons because of gravity. Because it's resting on the table, there's a normal reaction force, which we're going to need. And then we're applying our horizontal force of P. That's initially going to be 10 newtons. And then opposing that is going to be some amount of friction as well that we can work out. Right, so F has a limiting value of F max that we're going to want to work out. And then depending on the size of this force, we're either going to have acceleration in that direction or not. So let's work out the value of R first. So that's going to be found by resolving upwards into those directions. So F equals ma, resolving vertically, bearing in mind that there isn't any acceleration in that direction. So A is going to be 0 if we resolve that way. R minus 5g equals 5 times 0, which just means that R is equal to this 5g acting downwards. Okay, that's 49 newtons. Now we've got R, we can use our formula for F max, multiply it by the coefficient of friction, which is 0.4. And that gives us 19.6. Okay, just off the screen there, 19.6 newtons. Okay, so now we're pretty much done because for each of these we can figure out what's going to happen. So my maximum amount of friction is 19.6. If my force therefore is 10, this is for part A, that means that friction is going to equally oppose it in the other direction. It's going to be 10 as well. And that also means that there's no acceleration as well. Okay, because friction is kind of overcoming this, this force in that direction. So A will be 0. If our force in this direction is exactly 19.6, then this is the same value as F max. And what we say is that the object is in limiting equilibrium, if that's the case. I might write that down. So if this force that way equals F max that way. Okay, that's any greater force on P is going to cause the object to accelerate. So it's just on the point of moving. That's sometimes how it also describes it as well. Okay, and then part B is describing it. So the force is 19.6. Friction is going to be maxed out. And there you go, limiting equilibrium as well. It's on the point of movement. But also A will be 0 because it hasn't started moving yet. Right, thirdly, 30 newtons. That's clearly exceeding F max, so we're going to get some positive value of A in that direction. And then we're going to use Newton's second law again to work it out. So F is maxed out. Okay, it's can't go any higher than that. We're going to resolve horizontally using all the red stuff. So 30 positive, 19.6 negative equals 5A. Solve it and tidy up. So A is 2.08. Okay, let's do another example. Now, this is going to involve a little bit of trigonometry that's going to be a bit of a shortcut for lots of these questions. So just make sure you're paying attention to that bit. Right, similar setup, 5 kilogram box with a coefficient of friction of 0.5 this time, and we're applying our force at different angles, and we're seeing what the value of P is in order to get the box to accelerate. So here's the diagram. I don't need to draw the table in, but you can imagine it there, horizontally. 5G for the weight, R for the normal reaction. First of all, we're going to apply P horizontally. And then F is going to oppose it in that direction. Okay, so everything's in the nice directions. I don't need to do any splitting into components like we've been doing before. I'm just going to resolve vertically and find the normal reaction. And as before, there's no acceleration in that direction because we're on a horizontal table. So R is just going to equal 5G, and that's 49 newtons. So that means the maximum frictional force is half of that because it's mu times R. And that's 24.5 newtons. Okay, so that means if P exceeds this value, we can get the object to accelerate that way. Okay, right, now this is quite a common setup here with this tan theta business. So if P is applied at an angle of theta, where tan theta is 3/4, what you don't want to be doing now is doing inverse tan to get that angle, because that's not needed, okay? We like the fact that this is a nice fraction because it allows us to get the sine and cos values that we actually need as well. So please don't do that, because it's going to get a messy, nasty angle that you're going to get a lot of rounding errors and it's going to all be complicated. So don't do that. All right, so similar diagram. We're going to apply our angle theta, and that's the force P. And then we do need to get these components here, but we can do it using a bit of trigonometry. Okay, we know it's P cos theta, we know it's P sine theta, but what we need to do is get these in terms of fractions, which we can do. So if you think about a right angle triangle, you've got your theta down there. We know that tan of theta is 3/4, and that's opposite over adjacent, so we can fill in the opposite and adjacent with 3 and 4. And then from Pythagoras, we can easily get the hypotenuse, and you should recognize that as a 3, 4, 5 triangle. And then sine and cos we can do just by using the diagram. So sine theta is opposite over hypotenuse, 3/5. And cos is 4/5, 4/5. Okay, so that's preferable to doing the inverse tan like I said before. So use these instead. Now the PowerPoint's going to do decimals, but it's up to you what you want to use. So 0.8p is P cos theta, and 0.6p up there. Okay, right, now we're in a position to find the normal reaction force in terms of P. So we can do that. So resolve vertically. Now, This time r isn't going to be the same as 5g because you've got this vertical component here that's subtracting some of the force off of r. So we're going to need to do it properly. R plus 0.6p minus 5g is 0 because there's no acceleration that way. Tidy up, and that's in terms of p. Then we can times by our coefficient of friction, which just means halving it. So we get this, and this is F max. So this means that our horizontal component needs to now exceed this value in order for the object to move, and that's going to help us figure out a value of p. Okay, so that bit there needs to exceed this number here. We can set that up as an equation if you like. So we're now assuming that we're in, well, it's doing it as if it's in limiting equilibrium. So it's going to equate these, and then if p is any bigger, then we're going to exceed F max. Okay, so it's going to set this up. Right force is 0.8p minus these forces over here, and then it's 5 times 0. We're assuming no acceleration still because we're still having these things equal. Tidy up. And p is about 22. Okay, so that means that if p is any greater, then this force over here is going to exceed this force over here. Right. So we can still do this on an inclined plane. This is where we tend to be going with this thing. So if your plane is at an angle, we can still do all the same stuff, just making sure that all of your forces are in those directions that we like, which is parallel and perpendicular to the plane. Right, so this time we've got an inclined plane at an angle where tan theta is 0.75, which you'll recognise as 3/4. So we've got the same values of sine and cos that we had before. Sometimes you tend to get 5/12 as well. 5/12 is part of a 5, 12, 13 triangle. So those are really common, so look out for them. Right, coefficient of friction is 0.5, and it wants the acceleration of the particle. Right, so this bit we've done before, that's from the previous slide as well. We're going to fill in the rest of the stuff on the picture. We don't know what the mass is, so we're just going to put m kilograms. The mass is mg. This triangle here allows us to get parallel and perpendicular forces. Theta goes in there. Mg cos theta, mg sine theta. Normal reaction force. And then we've got a frictional force up the plane because our box is going to be let go and it's going to slide down, so friction is going to go up. Okay, bit of common sense as to which way things point. Acceleration goes down that way. Okay, so we're going to need to work out r first, then we can get F max. So we're going to resolve in the direction of r. We've also got this mg cos theta. No acceleration in that direction. All the acceleration is going in this direction. So that means that r equals mg cos theta. Cos theta we know, so we can put that in. That's 0.8. And then they're added to the picture. Right, now we can do F max, we can times by mu, and that's going to give us the maximum friction. So that's 0.4 mg. So that's maxed out up the plane, and then we're accelerating down the plane. Okay, now we're resolving parallel. We're going to resolve, usually wanting to resolve in the direction of A, so we're going to go down the plane. Don't forget about the little force down here that's acting in that direction. That's the one that we need. So the red stuff now. Mg sine theta points downwards, 0.4 mg points upwards, equals ma. Now the nice thing about this is that we didn't know what m was, but since every term has got m, we can cancel them out. So the mass is kind of independent of the acceleration. And then we can solve it for a, which is 2.0. Okay, everything on that left-hand side, we know what the value is. Right, one thing that might come up that you need to know about is about which way the friction points if it's in limiting equilibrium. So I'm going to write this down. So I'm going to say it as it will say it in a question, is on the point of sliding down, so if we have limiting equilibrium, but the object is about to slide down, on the point of sliding down, then friction is going to oppose that and point upwards. So that's the way friction goes in that case. If it's on the point of sliding up, then it's about to go upwards, so friction is going to point downwards. Okay, remember, it always opposes the motion of the object. Okay, so make sure you're pointing things the right way. All right, final example, and then we can call it there for friction. Right, okay, let's see what we've got. A mass of 4 kilograms pushed up a plane, that's going to be important as well, by a horizontal force of magnitude 25. The plane is inclined at 10 degrees, and acceleration is 2.5 meters per second squared. I want you to find out the unknown coefficient of friction between the box and the plane. Right, so we can do as much as we possibly can without knowing what mu is, and then we're going to end up with an equation that we can solve. Here's our picture, 10 degrees inclined, 4 kilogram box. I can go through this a bit quicker now, hopefully. All the forces go on. Remember, 25 is horizontal. We are accelerating up the plane, so pointing upwards for acceleration. This part splits into its components, 4g cos 10, 4g sin 10. This one is going to have an alternate angle in, because 10 degrees is going to be the same as this 10 degrees up here, because of the z angles that you can make. That's 10, which means that that's 25 sine 10, that's 25 cos 10. Now we're going to resolve to get the normal reaction. I need the normal reaction to get the value of f. So in these blue directions, we're going to get this. R minus 25 sine 10, because it points downwards, minus 4g cos 10 equals 4 times 0, no acceleration in that direction. So that's your value of R, and you can get that as about 43 newtons. Okay, now we can do mu R to get F max. So F max is 43 mu. Okay, we have to leave it in terms of mu. So that's going there, that's pointing down the slope. Now we're in a position to set up our equation in terms of mu, because that's the only term in the parallel direction to the plane that has an unknown in. So now we're going to resolve in the red directions. Resolve towards acceleration. So up the plane, 25 cos 10 minus 43 mu minus this one equals 4 is the mass and 2.5 is the acceleration. And then you rearrange it and you're going to solve it exactly for mu, 0.18. Okay, so the setup for these questions are quite similar. It just depends on what you're trying to find, and make sure that you're pointing things in the right way. All right, hopefully that's all right for you. You can have this PowerPoint if you want to have a look through at your own pace, and I'll see you next week. Thanks for your 13.